Okay, thanks for joining me. I'm super excited to look at one of my favorite topics in geometry, special right triangles. And before we get into what makes them special or why we have special right triangles, let's just remind ourselves that mathematics is the study of patterns. So we're going to take a minute and we're just going to try 3 problems that are right triangles. We've certainly studied right triangles so far, and you have an idea of how to deal with right triangles, and I gave you a little hint there. So I want you to just go ahead and solve these 3 problems and just let yourself notice and wonder, what patterns do you notice and how might that be significant? So I'm going to pause the video and you're going to grab a sheet of paper. If you don't have this paper in front of you, you can work on this paper, or you can just draw 3 triangles on your paper and do the math, and we'll meet up in a minute. Okay, I made some progress. I'm hoping you made some progress. Let's take a look at what we have. I want to remind you that our goal was to solve for x, the missing side length. So if I'm looking for this side length right here, I actually want to get x. So I'm going to take what I have, great setup, and I'm just going to take the square root of both sides. Square root and square cancel each other out, and I'm left with just x equals radical 128. We can do better than that. Let's rewrite that as radical 64 times 2. Or you could write it as radical 64 times radical 2. Radical 64 is 8 radical 2. And yes, indeed, you are going to need to remember your radical relationships here. So I'm getting 8 radical 2 right there. And if you do the same thing with this one, I'll just go ahead and give you the answer here. Y would be 12 radical 2. Make sure you understand where I'm getting that from. So that's 12 radical 2 down here. And then I went ahead and paused and waited on the last one. It's a little bit tricky, so let's go through. If there's one you were going to get stuck on, it's this one. Just check your work if you already did it. X squared plus x squared is not x. Okay, I'm not sure what just happened there, but hopefully it's okay on your end. So x squared plus x squared, I'm getting 2x squared for that. I must have accidentally hit to go to the next page. Equals 5 radical 2, quantity squared, I'm squaring both parts, so 5 squared is 25, times radical 2 squared is just 2, so 25 times 2, giving me 50 for that. And then I'm solving for x squared, so I'm just going to go one step at a time. I'm going to isolate the x squared by dividing by 2. X squared equals 25, and wow, that works out so nice. X equals technically positive or negative 5, but in this case, because I'm talking about side lengths, I'm going to keep the positive only, and we'll ignore the negative. Okay, so here's the part where I'm going to ask you to join me and be a mathematician. So how would a mathematician think? They would look at these 3 examples and they would say, wow, I notice things, and I know that you guys are very observant people and you're already noticing this. So the first thing that I'm noticing is, if we were to try to describe these triangles, what's in common with these 3 triangles? Yes, I know they're right triangles, but I think you can do better than that. So I notice that this has a 45-degree angle and a 45-degree angle. So if we have 2 angles that are the same, then we also have, yep, there it is, 2 sides that are the same. They're all isosceles triangles. Really? I don't believe you. Yes, they are. 12 and 12. Angles the same. And then this one, the sides are marked the same, and therefore we know the angles are the same. So if it's a right triangle and the angles are the same, both non-right angles are going to have to be 45 degrees. Agreed? Cool. Okay, so in a minute here, we're going to call this one. We're really creative in the world of mathematics. So we're going to call this triangle the 45, 45, 90 triangle. You okay with that? Okay, good, because you don't have a choice. So once we get that, now we're going to look at the relationship between the sides. I wouldn't have had you do Pythagorean theorem 3 times if there wasn't something that we could get at here that would be pretty cool and significant. So I'm noticing an 8 and an 8 for my 2 legs, and then I'm noticing 8 radical 2 for the hypotenuse. Here I have 12 and 12. Obviously, the legs are equal to each other. That's not new news. That's based on it being an isosceles triangle. But look at this. I've got 12, 12, and 12 radical 2. Is anybody seeing something here? Interesting. And I went backwards here, but I still had 5, 5, and 5 radical 2. Yeah, it's always going to work out that way. Don't believe me? It's okay. You're allowed to be a skeptic. Let's do something real quick over here. You don't have to write this down, but just for fun, to kind of convince the skeptics out there. Not a bad thing if you're a skeptic. It's a great thing, actually. It's where great ideas come from. Let's just keep this all general. So let's call this x and this x. It's going to be similar to what we just did right here. But let's keep it x and x. And then let's go ahead and just call this side C. So I don't have a specific number there. And what I'm going to do is I'm going to set up that same exact thing that I had. So I'm going to do x squared plus x squared equals c squared. And my goal is to solve for c right now. So I get 2x squared is equal to c squared. If I solve for c, it appears, is radical 2 times radical x squared. Well, what's radical x squared? Yeah, that's just x. So you have radical 2 times x. Let's write it this way with the radical at the end. And my side length here, my c, is x radical 2. How's that connect to what we just did? Well, didn't we just say if we had a 5 here and a 5 here, then we end up with a 5 radical 2? So if I have an x here and an x here, this is going to be x radical 2. The radical 2 is just going to be there. That's coming from the fact that we're taking the square root of this quantity. But that number that's in front of it, when you simplify your radical, is going to be the exact same as what your side lengths are. Every time. Pretty amazing, isn't that? Okay, so let's put that example on the side. And let's kind of bring this back into focus as much as we can. And let's get rid of that. Let's move down and write some conclusions. So my conclusions, you need to put this somewhere. So if you don't have this paper, it's fine. Just put them in a box star them, circle them, something. These are important. Okay, so we said we're going to call this the 45, 45, 90 triangle. And we know two things about this triangle. We know that the legs are equal. And again, that's because it's isosceles, not new. I just like to jot that down because I'm writing down all the relationships that I know. And then the other thing we know is we know that the hypotenuse is the leg times radical 2 is how I like to write it. I'm going to draw a picture and put on my picture what we were just looking at a minute ago. And my picture is going to be something like this. And I guess I'll write down what I know. So I know that these are equal. I know this is 45. And I know this is 45. I'll try to squeeze that on there. And then the relationship we have is that whatever this is, so I'm using L for my legs, then the hypotenuse is going to be L radical 2. Or if you wanted to do that with x's, you could certainly do that and do x, x, and x radical 2. Is a very, very common way that you'll see it done. Okay? So just to not confuse it, I'm going to go ahead and back up and keep it right here. But like I said, you do whichever one you want. Okay, so let's go ahead and try some examples and see how might this play out when I'm actually going to use it. So the whole goal here is to save some time. You saw that we could do Pythagorean theorem, so we could do the exact same thing that we did for those first three problems right here. I'm looking at number 1, and I'm noticing that I have a right triangle, and it's a 45-degree angle here, and I'm thinking through, okay, that's going to be 45 degrees. Cool, that means that these are equal to each other, and that means that y is 7. And I could go ahead and then do Pythagorean theorem, 7 squared plus 7 squared equals x squared, just like we did in number 1, just like we did in number 2. But we now know that the hypotenuse is going to be equal to the leg times radical 2. So if I have this common relationship, I know my legs right now are 7, therefore the hypotenuse x is going to be the leg length, which is 7 times radical 2. And if you don't believe me, do Pythagorean theorem. I'm done. That's it. Anybody on board? They like this? I know you like trig and I know you like Pythagorean theorem, but hey, you got to agree with me. This is a little bit quicker. Okay, cool. But we're not always going to be given the leg length, right? So let's take a look at number 2. Number 2, what's wrong with number 2? Nothing's wrong with it, but it's backwards because in number 2, I am given the hypotenuse as 21 radical 2. So here's the deal. Some of you are doing this in your head right now. Nothing wrong with that. Some of you are like, what do I do if I'm given the hypotenuse? I don't have a clue what to do. So I'm going to work it through as if you don't know what to do. I do know, first of all, that x and y are equal to each other, and that's cool. So then I really only need to solve for one, and then I'll know the second one. So let me go ahead and show you what I would do. I would start with this formula. Remember this formula that we wrote down? Use it. So the hypotenuse, I'm actually going to write it down, is the leg times radical 2. Or you can use, this is why I don't like to use x equals, or hypotenuse equals x radical 2, because I've already got an x in the problem, and sometimes the x isn't the leg, sometimes it is. So I like words, and now I'm just going to plug in. I either know the hypotenuse or the leg. What do I know? Yep, I know the hypotenuse, 21 radical 2. So 21 radical 2 is equal to the leg length is, well, leg length is my x right here, or y, whichever one you want to do, x times radical 2. Oops, this thing doesn't like to let me move things. Okay, so I've got 21 radical 2 equals x radical 2. What's my goal? Solve for x. So what am I going to do to solve for x? I'm going to do some algebra. What does algebra tell me to do? Yep, algebra tells me to divide, because I got to get x by itself. It's being multiplied by radical 2, so let's divide by radical 2 on both sides. That's gone, so I've got x by itself on the right side. Good news. So I've got x equals, sorry, indecision what color I want to use. X equals 21 radical 2 over radical 2. Well, that's convenient. Take a look there. The radicals cancel each other out, and I'm just left with 21. So it appears that x is 21, which we then said y was going to be 21. Does that make sense? Let's ask ourselves, well, if I said this was 21 and this is 21, then the hypotenuse would be 21 radical 2, right? Didn't we say that's the same as this number and that number? Make sense? Cool. It's nice to check our work going forwards, right? Okay, so how could this get harder? Well, sometimes we don't have numbers where we want, because some of you looked at, and I said, some of you did this in your head. You just saw the 21 radical 2 here, and you said, well, I'm just going to take off the radical 2. And yeah, we kind of did do that, but I'd ask you to ask yourself to think about, what did you mathematically do when you took off the radical 2? And that's where we get this division. So as long as you're thinking about it as dividing by radical 2, I'm okay with that thought. But you got to make sure you can do some that aren't as straightforward as that. So feel free to try the next two on your own, or maybe you're already doing these on your own. That's fantastic. Just double check that you got the same answers as me, So I'm on number 3, and I am going to keep talking these through so you can hear how I think about these. Number 3, so it looks like I've got the leg length there so I do know that x is 3 radical 2. That was a little think time for you, because those are equal to each other, so 3 radical 2 there. And then my y, well, that's my hypotenuse. So if you get stuck, write the formula out. Hypotenuse is the leg times radical 2. So I'm looking for the hypotenuse y. The leg is my 3 radical 2, so it's 3 radical 2 times radical 2. And this was my leg length that I know. So the radical 2 is already there in the leg length, but I've got to multiply by radical 2 from the formula. So 3 radical 2 times 3 radical 2, I got to simplify it for my answer right here. 3 radical 2 times radical 2 is 3 times radical 4, which is 3 times 2, which is 6. So those are my two answers. Yeah, that one's a little bit different, isn't it? Okay, take a minute to digest that one. Make sure you're okay with it, and then we will move on to number 4. Okay, last but not least, and I'm going to squeeze this in, find room for this. So this one, I'm given what? Yep, given the hypotenuse. So I've got the hypotenuse. Oh dear. The hypotenuse is supposed to be something radical 2. Isn't that what we said over here? Because I figured out that I could just take off the radical 2. Divide by radical 2, and then just get this number in front. But there's not a radical 2 here. Okay, so can I tell you my favorite mistake that students do? I'm laughing as I'm thinking about it. Students like to do this, and they just say, well, that was supposed to be 10 radical 2. Clearly, Miss Fisher is losing it. Let's just make that 10 radical 2, and then we can say x is 10 and y is 10, right? Wrong. So I do make mistakes. This isn't a mistake. This is intentional. If the hypotenuse is 10, we got to be able to work backwards and figure out what the leg lengths would be. So what do we do if we're stuck? If we can't do it in our head and just figure it out? I do know these are going to be the same, by the way, so that's helpful. Yeah, I go to my formula. So let's use our formula. So hypotenuse equals leg times radical 2. Remember how we did that over here? Right here, doing the same thing. So now I'm going to plug in what I know. The hypotenuse, I know that. That's 10. So the hypotenuse is 10 here. And the leg length is, well, I don't know it, but I'll just use x for my leg length. So the hypotenuse is leg times radical 2. Means 10 has to be, think about it, 10 has to be something times radical 2. Whatever this is, multiplied by radical 2. And it's going to have to give me 10. So this allows me to think algebraically, because now I have an equation, and I don't care how much you hate triangles. You can look at this equation and say, I know how to solve that. I'm just solving for x. It's x times radical 2. How do I undo multiplication? Sure enough, I divide by whatever it is that's being multiplied. So I divide by radical 2 on both sides, and I get x equals 10 over radical 2. So I'm done, right? 10 over radical 2. Kinda done. What's wrong with that? Yeah, some of you are already seeing it. Thanks for being so observant and remembering what we've talked about earlier this year. we decided that we didn't like radicals. It's not considered simplest form if we have a radical in the denominator. So we're going to take this 10 radical 2 and we're just going to fix that up a little bit to put it in an acceptable form, or let's say simplified form, because that is technically our answer, but we're going to simplify it. So how am I going to do that? Yeah, hopefully you're remembering this process called rationalizing the denominator for putting a name with it. If you don't remember that, but you remember doing it, that's good. So I multiply across the top, 10 times radical 2, and across the bottom, be careful, radical 2 times radical 2 is not 4, it's radical 4. And radical 4 is really just 2. So that's going to give me 2. Whoops. This combined here to give me the radical 4. And that just gives me just 2. And I'm almost done, but 10 radical 2 divided by 2, I can simplify that. The 10 and the 2 can divide, since those are both outside the radical, and that gives me a 5 over 1 is the same as 10 over 2. So my final answer here is going to be 5 radical 2. Oops. So remember that x and y were equal to each other because those are my legs. So the good news is that your hard work pays off because you get to use it twice. Hopefully that helps. I think I gave you just about every case I could, so that should help you for sure with the practice problems that you're going to do for follow-up with this, and basically gives us the opportunity to solve knowing just one side length. So big picture here, just one side length. This is the first time that we've ever solved a triangle knowing just one side length, except for when we used what? Yeah, when we used trig, we had to have an angle and a side length. Well, we technically have that here, right? Because we do have an angle measure. We actually know this angle, and we have talked about the fact that that's going to be 45 also. So we know an angle and a side, and trigonometry would be the other thing we could do. You could certainly set up a trig equation here, and you could solve for x and compare, and it should give you the decimal approximation of 5 radical 2. So then the question is, and this is worth like 30 seconds of thought, why would we use special right triangles instead of trig? So I'd encourage you to ponder that for a second. Hopefully you came up with a couple thoughts maybe. Some of you might be thinking that it's way easier and you don't have to, I would anticipate some of you actually did all of these in your head and didn't have to write anything down. You also didn't have to use a calculator, I'm hoping. And we have to use a calculator or a trig table for solving trig problems. So that's for sure a benefit. And the second thing is that our answers are in exact form. And I know you don't necessarily appreciate this as much as you will eventually, but our answers are not rounded answers at all. They are exact form. And trig does not give us the ability to get exact answers. So that would be the second reason that this is a really powerful thing. And this is going to appear in many classes after this one. This is not a geometry specific thing. So super important that we get a good handle on this before this year's over, because it's going to come up next year and it's going to be the foundation of your pre-calculus course that you will take. Okay, thanks for joining me. Good luck with your practice on these, and don't forget to watch the second video for special right triangles part 2. Fourth, that's 2x squared